Welcome to the Geology Lecture Series at SWOCC, live stream from the Geology Lab in the new Umpqua Hall. So I'm just going to give you a quick rundown of some of the upcoming talks. They've really been coming together in the last couple days. Tonight's talk is going to be fantastic, our Cascadia Anniversary Lecture with Chris Goldfinger. Next, about just under 2 weeks, on Tuesday, February 8th at 7 p.m., we've got lessons from the School of Hard Knocks, from the ozone hole to global climate change, with Sean Davis from NOAA. I don't have a specific date on the next one, but the health effects of air pollution, why do we care? And the date hopefully will be March 8th. But we're still in negotiations there. It's with Dr. Tong Zhu from Peking University in Beijing, and he is this year an American Geophysical Union College of Fellows Distinguished Lecture Series speaker. It's a new lecture series that they put together that only comes virtually, so it fits the current mode. In the spring, we've got 2 dates already, and a little bit of question whether we'll get to a point where we can come back live and we can get together in the Hale Center for the Performing Arts, or whether we'll need to continue virtually. But the first one is Saturday, April 16th in the afternoon, currently scheduled 1 to 4 p.m. It's going to be an Alaka conference, and Alaka is a native word for sea otter, and this is going to be a sea otter conference honoring the legacy of Chief Donald Boyd Ivy, who we lost last summer. The speakers that are currently involved include Bob Bailey from the Alaka Alliance, Bobby Hall, Emeritus Faculty from Oregon State University, an archaeologist, a current member of the faculty at Oregon State, Lauren Davis, also an archaeologist who has worked the geology or archaeology of the South Coast pretty extensively, also working with my friend Don Ivy when he was alive. Bill Robbins, there's an Oregon State connection, including tonight. Bill Robbins is the author of Hard Times in Paradise, Coos Bay, Oregon, 1850 to 1986. And we're looking for a few other participants that we expect to round that out. Essentially, sea otter and a sense of place on the South Coast. And finally, Saturday, May 21st at 7 p.m. I'm not able to release the speaker or topic yet, but we have confirmed somebody for that particular date. Just have to iron out a couple of little details. So I mentioned we're here tonight celebrating a fantastic anniversary. So most of you know what that anniversary is. My mom and dad decided to get married a few years back on this date. They didn't know at the time it was also the anniversary of Cascadia. So mom and dad, happy anniversary. I know this is a great anniversary present to host a talk on your anniversary for you. So again, most of you know this is also the anniversary of the last great Cascadia megathrust earthquake. And that took place about 2 hours forward, so at about 9 p.m., January 26 in the year 1700. And over the years, this has become a very important talk for me to host in the Geology Lecture Series, because it essentially serves as an annual reminder that we need to be aware and be prepared for the next great earthquake, tsunami event in our region. And so one of the things about that, I've been here 26 years now. When I first arrived, we didn't have much awareness that great events such as this could occur. I think the majority of us recognize this now, and now we have to transition into that preparedness piece. So when events like Sumatra and Tohoku, and even the recent Hungatunga eruption and tsunami warning occur, it's a continuing reminder that we must be alert in our area as well. And I also use those events personally, and also this talk as an annual reminder, however large or small, when a quake or tsunami happens, consider adding objects to your to-go bags and or other disaster supplies that you're hopefully accumulating. If you don't have a go bag and aren't accumulating disaster supplies, hopefully this talk will be an impetus for you to get started with that. So this evening, it is my great pleasure tonight to introduce Dr. Chris Goldfinger. Chris received his BA and BS from Humboldt State University, his MS and PhD from Oregon State University, and that is where he is now a professor in the College of Earth, Ocean, and Atmospheric Sciences. He's also director of the Active Tectonics and Seafloor Mapping Laboratory. Chris and his team have done some of the groundbreaking research on Cascadia, including generating the relationship between the turbidite sequence, or deep sea sediments, on the ocean floor with the pattern of Great Cascadia earthquakes. He was also kind enough a few years back to delve deeper into the sediment record, allowing an understanding that on the south end of Cascadia, here in Coos Bay, North Bend, we have a greater probability of a major event than in the north. That's a topic I'm sure he will address at some level tonight, so I won't go further. I could go on about his accolades, his publications, but it gives me great pleasure in welcoming tonight the speaker for our 17th annual Cascadia Anniversary Lecture, Dr. Chris Goldfinger. Chris?
Hi, Ron. Hello, everyone. Thanks for the lovely introduction, and welcome to the anniversary of the Cascadia earthquake. I guess it's a sort of an anniversary only a geologist could celebrate, but here we are, and so I'm looking forward to showing you a little bit of the history of how we came to know about Cascadia and some late details, and then a little bit about where we stand in terms of our society living on top of this thing. So thank you, Ron. Should we go ahead and start up? Let me share my screen and just take a second. Okay, there we go. So I'd like to just acknowledge a whole host of people. Probably more than 100 people have worked on this over the years, but some of the key people are noted below. Co-chief scientists, collaborators, students, and technicians, and ship's crews from some of these cruises listed down here. And so let's just go ahead and start here. So almost everybody's seen the Big Bang Theory by now, and maybe some of you noticed that that Sheldon, one of the main characters, doesn't really care much for geology. He's a big-time particle physicist and talks about string theory and things like that. And he kind of rags on geology as being the Kardashians of science, or just beer and guessing is another way to put it. And the funny thing about there's a lot of accuracies in this show, and one of the funny things about this is Sheldon is right. And as a geologist, I can say that. So geology is about 100 to 150 years behind the other sciences. And so, I'm going to have to change something. I've got timing set up on this. Hang on just one second. Oops. Sorry about that. Timing's off. And we'll go back here. And there we go. So anyway, there are a lot of reasons that geology is so far behind. But it's really kind of stunning. So you think about it, 53 years ago, more or less, Armstrong and Aldrin were hippity hopping around the moon, and in 1969. And this is arguably the most advanced thing that humans have ever done. And at the time, plate tectonics, the theory of everything in earth science, was 6 years old. Before 1963, we really didn't know where mountains came from, where volcanoes came from, or any of the really big fundamental things about the Earth. And all the explanations essentially up to that point were sort of like the stork brought it, explanation for toddlers of where babies come from. And that sounds crazy to non-geologists. It sounds crazy to me too. But it is what it is. And here's just for fun. Here's Aldrin setting up a seismometer on the moon, and below that is a moonquake uh, measuring the impact of the lunar module from Apollo 12 when it hit the moon. So we don't have to go very far back in history to look at Cascadia and its role in plate tectonics. It actually played a key role in the development of seafloor spreading, this new theory of everything that became plate tectonics. And so it was recognized as one of these new things called a subduction zone, where one plate dives under the other. Um, way back in 1961 was when the paper about that came out. But Cascadia had a problem. Most other plate boundaries in the world fit the new idea of plate tectonics pretty well, so well that the whole theory was really accepted with great speed in just a few years in the early 60s. And people zoomed around the world explaining and learning about this new plate boundaries and how these things matched up to the new theory. But there was a little bit of a problem. Cascadia was one of the instrumental sites that helped demonstrate this thing, but it was missing one component. It had an obvious plate boundary. It had obvious volcanoes that were related to the plate boundary, and those were known to be more or less active at the time. But what it was missing was earthquakes. There just weren't any earthquakes to speak of on a daily, monthly, yearly basis, and so that baffled people at the time. And so I think most scientists sort of tippy-toed around this and ignored it for quite a while. But that only lasted about 20 years or so, and then eventually people had to come back to Cascadia and explain this oddity, the one plate boundary of the world that did not seem to fit plate tectonics. And in 1984, Canadian geologist named John Adams was really the first to suggest that direct evidence of Cascadia earthquakes existed in the form of turbidites, which are just deep sea landslide deposits, sometimes triggered by earthquakes, but also triggered by other things. And and that his abstract at that time, and and also another paper by some famous seismologists, Tom Heaton and Hiro Kanamori, suggested that maybe Cascadia was similar to Alaska and maybe similar to southern Chile, which had had giant earthquakes in 1962 and 64, or 1960 and 64, sorry. And, maybe Cascadia, even though it was presently quiet at the time, had similarities to those places. And so the alarm started to go up in about 1984, 85 or so. And people began to collectively go, uh-oh, maybe Cascadia is just quiet for some other reason. And in 1987, Brian Atwater, who's now world famous for this discovery, discovered deposits that look like this, and in Willapa Bay. And this doesn't look particularly, I mean, it looks odd, but not particularly striking. It doesn't scream earthquakes, but Brian was a good marsh ecologist, and he realized that the marsh plants growing up on top in the modern marsh were the same species as are recorded in this black layer of peat. And this black layer of peat was a few hundred years old, but the same species as the live plants up here. But he also knew that these plants couldn't exist that far apart vertically because of their tide tolerance and their tolerance to salt water. So something happened between this time at the top and this time down at the bottom, and then in between are some other odd things. Here's some gray mud. This is sort of subtidal bay mud, which really doesn't belong there. And then there's a sand sheet here, a very clean marine sand sheet with marine fossils, not river source, but marine. And so Brian rather boldly decided or interpreted this as the downdropping of the entire Pacific coast of about a meter during a giant earthquake in the past. And at first, nobody really believed it, but Brian carefully went through the evidence here, and his idea was sort of the last man standing. And some of the details are that so this intertidal mud, sure enough, is deposited when this is below tide level. This is an entirely marine deposit. This sand sheet, it not only has marine fossils in it, but it thins inland. So it's sourced at the coast, brought marine sand in, and thins inland, but it goes kilometers inland. So this was most consistent with a tsunami sand sheet. And then the peat below here, some of these divots in it turned out to be Native American fire pits. So there were people here when this event happened, whatever it was. But it happened quickly, and you can see, even in this slide, you can see the very, very sharp contact between the old peat deposit, which was a marsh, and the sand sheet. So he reasoned that this thing happened very quickly, and rather than sea level coming up over a long period of time, the land went down in just a matter, really, of minutes. So that was a remarkable hypothesis, and it took a little while to be accepted, but the sort of nail in the coffin of this hypothesis came not from Cascadia, but it came from Japan. And a colleague, Kenji Satake, looked at Japanese tsunami deposits from a tsunami that arrived on January 26, 1700. And this tsunami came in, just rolled in without any warning at all. And the Japanese, of course, were really familiar with the pair, the earthquake-tsunami pair. And this tsunami rolled in with no warning at all, no earthquake, and did damage in warehouses along the coast. And so with some careful sleuthing and reading old characters and whatnot, Kenji was able to get the water heights pulled out of these records and mapped them out, and then tested as a source other subduction zones around the Pacific. And he found that Cascadia was the best fit for those. And so here's a simulation of the 1700 tsunami coming from Cascadia. And so that's how we know the date of the last event, January 26, because of the written records. And the written records were detailed enough that we even know the time of day. So we know the time of day in Japan, and if you back calculate the deep water wave speed, we come up with about 9 p.m. local time in Cascadia as the real time of the last earthquake. So about an hour and a half from now will be the real anniversary. So during these big earthquakes, a lot of things happen, and I'll want to flash back just a little bit to the 1960s, when some OSU students, these guys here, Hans Nelson, Gary Griggs, John Duncan, and 2 UW students, Bob Carson and Bill Barnard, were taking cores offshore in deep water in Cascadia Basin. And these guys were sort of dyed-in-the-wool sedimentologists. They were interested in sediment transport, one of the most boring things on the planet as far as I'm concerned. But they were meticulous, and they studied this in great detail, not so much considering plate tectonics or earthquakes or any of these sorts of things, but the sedimentology of these landslide deposits that were coming down and filling up Cascadia Basin in deep water. And this was their tool, ships like this, 1960s vintage Yaquina was the Oregon State ship, and the Tommy Thompson was the UW ship. And at the time, they found these deposits offshore, and they mapped them out in great detail, did the sedimentology, the grain size, the heavy mineral analysis, and lots of things, and filled up 6 PhD theses that are each about, and these were, in the day when they had to hand type these things, and they're about 2 inches thick, weigh about 5 pounds apiece, and they're just full of table after table after table of data from Cascadia. And so their conclusions of their theses were simply that sediment rolled downhill and filled up Cascadia Basin, just to put it simply. And they filled out, they told a lot of detail about that. And they also speculated, and their advisor was my advisor much later in time. They speculated about subduction zones, this new thing that was just a few years old, and they speculated about earthquakes and things like that. And they were advised by Vern Kalm, their advisor, to don't say anything about that and don't try to publish it because nobody will believe it. And that turned out to be a big mistake. So a few years later, John Adams, the Canadian geologist, wrote his abstract not a few years later, in 1985, and proposed that the submarine landslide deposits that these fellows found in the late 60s were evidence of great earthquakes. And here's the original figure from his paper showing channel systems in Cascadia. And his reasoning was basically this. Mount Mazama had blown up about 7,600 years before. It had spread ash all through the Pacific Northwest, and that ash had been distributed out onto the abyssal plain and margin by the river systems of the Pacific Northwest. And the first thing he noticed, which was actually noticed by the original investigators like Gary Griggs, was that if you counted down from the top, these submarine landslide deposits, or turbidites, contain the Mazama ash. But not only that, they contain the Mazama ash in the 13th turbidite down from the top. That is, it first appeared in the 13th turbidite. And that was true up in Washington, in Astoria Canyon, and down here in the Rogue system as well. And so that struck him as a really bizarre coincidence, because turbidity currents can be triggered by storms, earthquakes, distant tsunamis, a pretty long list of other things. And so if it was a mixture of all those things, you'd expect different numbers at all these different places. They would be just sort of random. But that's not what he found. There was just a tremendous coincidence of similar numbers of events all up and down the margin. And so that caught his attention and caused him to start thinking about earthquakes, because a really big earthquake extending the full length of Cascadia would be a really simple, elegant way to explain the similar numbers of events, simply 13 big earthquakes in a row. And so that's what I call the coincidence test. What are the chances of this happening randomly? Well, it's not really something you can calculate, but you can imagine the odds are pretty low. But he went a bit further than that, and he noticed that there was a confluence of these channels. This is Willapa Channel here, coming out of the shelf near Willapa Bay, and Juan de Fuca Channel going off here toward the Juan de Fuca Strait. And they come together at a point right here. And he noticed that on one side of the confluence, you had these 13 or so post-Mazama turbidites, and on the other, you also had 13. But when you go to the confluence, and then you go downstream from the confluence, you still have 13 down here, and you still have 13 down here. Well, so that led him to, that there's a sort of a binary choice here. Either one of two things happen. The first thing could be that at the confluence, just below it, where there didn't happen to be a core, you would have 26 turbidites, and then you would just, by attrition, you would lose 13 going downstream, and it would be just a giant coincidence that you had 13 here, and also maybe a coincidence that you had 13 over here. But the other option is that these 13 turbidity currents came down these channels synchronously, arrived at the confluence at the same moment in time, merged, and then went on downstream, and that's why you have 13 here, and everywhere else. And that's what he proposed. And this is a very simple thought experiment, really. John Adams never went to sea, never even actually looked at these cores. He was using faxed core logs from OSU. And he came to this conclusion, this very elegant conclusion. And it sounded to many of us in the community, I was a graduate student at the time, it sounded crazy. It sounded far too simple. It sounded like the musings of a land geologist, desk musings of a land geologist, and it couldn't really be that simple. So I wound up working with a colleague named Hans Nelson, who was one of those original OSU students. Later in his career, he came up to me at a meeting and said, "Hey, have you read this paper by John Adams?" And I said, "Yeah. What do you think of it?" And he said, "Oh, it's wrong. It's just flat out wrong. I worked out there, and the 13 turbidite stuff is just nonsense. It doesn't work." So he talked me into writing a proposal to go disprove John Adams. And so we did. Well, we wrote the proposal anyway. So we went out to sea, collected a whole bunch of new cores, which are the gray ones here. The white ones are the original 60s OSU cores. And then green ones and red ones and so forth were all collected in a few cruises in the late 90s and early 2000s. And we started in the middle of Cascadia, or north middle at Astoria Fan, the area where Hans Nelson was the expert. And then we moved up to Washington and the Canadian systems, and then down to the south afterwards. And then in the middle of that cruise, we pretty quickly found out that we were wrong and John Adams was right. So sure enough, these systems did have 13 post-Mazama turbidites, and there were simple explanations for why Hans, who was an expert in this, had thought that Adams was wrong. Too much detail to dig into, but we were a complete failure, and a lot of scientific discoveries and advances come out of failure, and this was a big one. And so in the middle of this cruise, we realized that we had failed to disprove Adams, and we sort of became reluctant paleoseismologists. We thought, well, if this actually works, maybe we should dig into it and see what happens. So we did. So a big part of the project was creating a modern bathymetric map. In the 60s, they could hand draw a contour map, and it wasn't very satisfactory. And so a big part of this was just building a map so we would know where to go. And at the time, much of the data was classified by the US Navy, and there were big chunks that didn't exist. So a huge part of this was basically creating the map that you're looking at here. It took several years. So what actually might happen during an earthquake? This is sort of a cheesy animation of John Adams' hypothesis, and here it goes. You shake the entire margin synchronously during an earthquake in over a couple of minutes, and over about a half a day's time or so, these turbidity currents will run down the deep sea channel systems and lay down their deposits for future geologists to come in and collect them. And Adams' hypothesis was that this happened synchronously at least 13 times in the last 7,600 years. So since this seemed to be working in crude terms, we started becoming paleoseismologists and looking at some of the details and where you could get these records and where you couldn't. And it turned out that Hans's original reluctance about this came from simple site selection. Some of the sites that he had chosen to look at just weren't good sites for accumulating this record of great earthquakes. And here's just a picture of Astoria Canyon showing that the submarine canyons have all the details of modern river systems, and with good bathymetric mapping, you can use these just like air photos and look at the details of here's a point bar in the channel system, and here's one of our core sites, and so on, and figure out where you go precisely to get these kinds of records. And so so here's sort of the modern view of the systems that we use. This is a core logger that collects density and magnetic properties and other properties of the core systems. This is one of our techs that came on this cruise, Francois Charlet. And so we run all the cores. These cruises are sort of like a whaling cruise. We're just a processing ship to get the cores, run them through all of these scanners, collect all the data, and then put it together later. And so a typical core sample, if we look at it, the result of that machine is a diagram that looks like this. These are X-rays. These can be X-rays or CT scans are more common now. And a hand-drawn diagram of the deposit itself. This sandy, multi-layered sandy thing is the turbidite, and the light colors in the X-ray. And then these wiggles here are the physical properties that are collected from that machine. So here's magnetic susceptibility here, here's grain size in the purple, and here's just density here, and here's P-wave velocity of the sediment. So what these basically show is everywhere there's a kick in density and velocity and magnetic properties, that's where the sand is. So these represent sandy pulses in these turbidites. And here's just another example on the right that has 3 kicks in it. and 3 sandy layers that you can see. And so this is, this is just like using X-rays on a person. You can see the leg bone and the joint, the knee bone and all the details, and start to look at the details of this. Well, how does that actually help anything? We knew the deposits were there, but we'll come to that. And so here's now the modern view of it. Here's a CT scan. So this is sub-millimeter resolution, looking at the whole deposit. Here's just the sandy part of it. Here's the silty part of it, and here's the clay part of it. And you can see just tremendous detail. Here's a very fine burrow of a burrowing organism in the silt. And so we use these things to pull apart the details of the deposit as it was laid down, and the boundaries between these deposits and the sediment that was deposited between earthquakes. And that turns out to be pretty important. So we borrowed some techniques from the oil industry. We were after the same thing that John Adams was. We wanted to see if these things were synchronous. And John Adams' elegant test, it turns out, works very well. It passed the test. But it's a little bit unsatisfying in the sense that we didn't know the timing of these events, and we wanted to throw some other tools at it and see what would happen. So we used some oil industry methods, because the oil industry investigates turbidites in great detail. They're the host rocks for oil deposits. And so some of the most commonly used techniques in the world are called well log correlation. So you can track an oil deposit from one very expensive well to another spot where another very expensive well would be drilled. And so we used their methodology. They've been doing this since the 1920s, and they have a lot of money involved and a lot of resources trying to do the very best job. And this is the method that they use. They don't publish anything because it's all proprietary. So, but luckily, some people at OSU had been trained in these methods, working for Chevron, and they taught some of the students of the day, which included me. So we were able to do this, and here's just an example. These two cores have these wiggle physical properties of density and magnetics and so forth. And the CT scan and a RGB image shown here for each one. But these two cores now are 250 kilometers apart. One's in Central Oregon at a place called Hydrate Ridge on the left, and the other one is in the Rogue system, in the Rogue Canyon. And you might be able to look and just kind of scan down this thing, but to a trained eye, and maybe even to an untrained eye, it turns out that these sequences are almost identical. Not only in their radiocarbon ages, which are shown off to the side here, and are maybe hard to read on a small screen, but in terms of the wiggles themselves. They're sort of fingerprinted. So here's an example. This is T11, one of our big events. And this event is big and ubiquitous and has a sort of a unique shape to it, up and down the margin. And so individual events can sometimes act as individual fingerprints. The sequences of events, like a medium, small, giant, that sequence is ubiquitous as well, and can include subsections of these or the entire core. And most often, it's the entire core. So we found as we went along that not only could we use John Adams' confluence test, but we could look at the sequencing of these things. And while we couldn't prove synchronicity quite as convincingly as he did, what we found was consistent with his hypothesis. And so here's just an example. Here's that same big event, T11, at 4 different core sites. And you can see there's a lot of differences, but there's also similarities. It sort of has a characteristic molar tooth shape to it. And what this is it just represents how much sand is in the deposit. So this is the density trace. And this is just representing sand quantity. So if we look at these 4 examples in context, here they are. They stretch the full length of Cascadia from Juan de Fuca Canyon in the north to Rogue Canyon in the south, not quite the full length, but almost. And here they are in context. And so when we date that single event, it's 5,900 years plus or minus 150 or so at every example. And so we also, like Adams, had the Mazama ash. Here it is. It's absent in one core that has no access to land sediment sources. So it's missing there, but present here. And so maybe what you can see then is a building story about the offshore stratigraphy that turned out to be pretty consistent. And so here's a figure showing some more examples of that. The middle panel is Hydrate Ridge off Oregon and Rogue Channel, Southern Oregon, with that matchup just colorized that I showed you a minute ago. But here's another example, Rogue Channel versus Cascadia Channel. These are a couple of 100 kilometers apart. And there's no physical connection between these things at all. That's an important detail. And here's Rogue Channel and Juan de Fuca Channel. Now these are about 400 kilometers apart. And so we kept making more and more diagrams in this sort of oil field methodology, and we kept finding good matches between them, not only with the radiocarbon ages, but with the sort of fingerprint wiggle matching that we saw. So it's hard to look at those and say, oh yeah, I see that relationship, just looking at those wiggles in a talk in this format. It took us a couple of years to spot them and play with them and just generate those slides that you just saw. But here's a simpler way to look at it. So for those same 4 sites that were in that animation that I showed, Juan de Fuca, Cascadia, Hydrate Ridge, and Rogue, these stretch 3/4 of the length of Cascadia. And what these black bars represent is just the thickness of the deposits from the top of the core down to the base of the Holocene, which is 10,000 years ago. And so what I'm going to do is just show you a simplified version of this sort of testing for synchronicity by matching up these deposits along strike. So the thickness is shown by the thickness of the black bar, and these are real values. This isn't an animation. These are the real values. So the first thing I'm going to do is just, well, it's already done in this slide, is just stretch the cores so that the tops and the bottoms are even, so that the surface at 0 time is at the top, and the bottom at 10,000 years is at the bottom. So the cores in real life are actually slightly different lengths, but now they've been stretched so that they match a time scale. And so now, those same beds, those 19 beds, are now shown with the base of each one flattened, which just means shown at an even time scale across the diagram. And so that means the base of each bed is matched to the base of its potential correlatives at the other sites. And now you can see something kind of remarkable happens. They start to look, the sequences start to look similar. And now if we do the same thing to the top of each bed, then it looks like this. So this is just basically hanging these events on an even timeline so that their bases and tops match across time, which is on the y-axis. And and so this is not a definitive forward model. This is a test of whether these things could be the same or might be different. And so it doesn't have to work at all. If these stratigraphic sequences were different, this would just look like nonsense. They wouldn't match. But in this test, you can see that they wind up as pretty effective barcodes and look virtually identical across the margin. And then if we do it matching them to a true time scale shown on the left and add the radiocarbon ages, it basically looks the same, but spread out just slightly differently. And so there it is. This is the barcode test, sort of a newish test of whether these things could be synchronous. And it's still not as good an accuracy test as the confluence test, but it shows that these sequences of the big events up and down Cascadia margin are virtually identical. They're the same number of events. The time, the spacing in time is the same. And it's just one of the coolest ways of visualizing this sequence. And I'll show you just one more example of that, get even a little more geeky. So here's again on the left, Hydrate Ridge off Central Oregon and Rogue Apron on the right. And we're going to look at some details of that. Here's some of the major events, just major correlative events, the ones that I think match the best, shown in purple and green. And then let's zoom in on that in detail. So here I've made the same kind of barcode, just using the bed thickness for each of these events. And the radiocarbon ages here, there isn't a time to examine this, for you to examine this super closely, but the radiocarbon ages are consistent. They can never prove synchronicity, but they're pretty consistent. And so then and so there are the event numbers. We call them T5 through T13. And then let's just take out the barcode part and look at that without all the complex data. And here again, you can see that the sequences are almost identical. There's some slight differences here because this diagram includes some events that are of different length and they don't run the full margin. So this event here, for example, doesn't make it all the way to Hydrate Ridge and so on. So there's some small differences that you'll see in the next few slides. But this just kind of blows me away at how similar these sequences are. And so another thing that's been done in recent times was to kind of throw the book at Adams' confluence test and see if it really holds up to modern scrutiny, as well as it does as a thought experiment. And so here's the confluence. Here's Willapa Channel. Here's Juan de Fuca Channel. The white dots are the cores that Adams had at his disposal at the time in 1985, and all the other colored dots are the cores that we have at our disposal now. So we can build a much tighter story and examine this in a lot more detail to see what happens. So it turns out that the big confluence here that Adams used is not the only one out there. In order to pass Adams' confluence test here, it also had to pass a confluence test there, and there, and there, and there, and there. So and Adams and folks of that day didn't have this sort of detailed bathymetric data, so they didn't really realize what a tight system this thing really is. And so to pass the confluence test, it has to pass really 6 confluence tests simultaneously. And there's even another one off screen down there. And so we went in with sidescan sonar and collected modern bathymetry data and sidescan data to look in detail at the pathways of these things. And here's Juan de Fuca Channel being somewhat blocked by the thrust fault at the toe of the Cascadia wedge and depositing this dark mud behind it. So it's showing that this channel is active today in a dynamic sense. We examined some alternative pathways that were actually proposed by Brian Atwater in 2014 or so. And we did this with hydrodynamic modeling and so forth. So the dashed line was something that he proposed to sort of short circuit the confluence test. And it turned out that this pathway doesn't really exist. There are mountains here in a place where Brian thought that there was a pathway through there. So we tested that explicitly, and that was found to not work very well. We did this with hydrodynamic modeling, and I think this is get this video going. So what this does is basically takes these core samples that you saw there, and in a Bayesian sense builds a model that fits the core data with a turbidity current that could be responsible for that regional distribution of the deposit and the final deposit. And so we ran thousands and thousands of these models to find the best fit solution in order to really learn more about the pathways and where these turbidity currents could go and where they don't go and so forth. And so, at the end of this investigation, the sort of testing of John Adams' idea, what we found was that we could easily correlate deposits from one side of the confluence to the other side. It was as if it wasn't there. The wiggle matching worked really well, implying that the source was very, very similar, if not the same. And we extended his sort of turbidite count from post-Mazama back to the beginning of the Holocene, where they're typically 19 or 20 instead of 13. And we found some exceptions to it that were clear reasons for. Those are the ones shown in red. But these two numbers are the Holocene count on the left and the post-Mazama count on the right. And so we found that John Adams' original work was quite good, and the numbers were only slightly different than his. And then we found a little helper. So we found that the mineral provenances coming to the southern part of this were different than the ones coming to the north. And one of the key bits was a mineral called glaucophane, this little blue guy down here, which is present in the north, not present in the south, which was full of other magnetite and other mineral assemblages that characterize the Columbia River source versus the Fraser River source. And so when we looked at the heavy minerals and we did some more heavy mineral analysis, we found that the northern section shown in blue and the southern were very distinct and very separate. And we found glaucophane where we found the green checks and not where we found the red checks. So these things were very distinct. There was no short circuiting of the confluence test in this area, and they remained very distinct until they met, until we got down to the confluence where we found individual turbidites had a mixed signature below the confluence in individual deposits. So basically, Adams' hypothesis hit a homer and held up very well to modern analysis. And then one of the nicest things in science is when an independent group goes out and tests your ideas with their own gear and their own reasoning and own methodologies. And so a group did that, Tark Hamilton, Randy Enkin, and a group of others, Audrey Dallimore, Canadian Geological Survey, were pretty skeptical about this whole business. And so they went out and tested it off Vancouver Island. And what they found was a near perfect correlation between sites in Effingham Inlet and a place called the Slipstream Slide and our sites at Juan de Fuca Canyon down at the south. And so this is published in 2015 and and did a really nice job of not only corroborating what us Americans found further south, but extending the record up to the limits of Cascadia in central Vancouver Island. So the bottom line is, in 2022, on the anniversary, there's a tremendous amount of paleoseismic data out there. And this diagram, we call it a space-time diagram, attempts to pull out that all together. It's a horribly messy diagram. Looks beautiful to me, but probably less so to you guys. But this is all of the land data and all of the marine data on the same diagram. And the attempt is to look at this and see if there's a coherency between all these different types of data and whether you can, whether this is a hodgepodge group of earthquakes or mixed sources, or whether there's actually a coherent signal here. And what we concluded was that the signal's pretty darn coherent, and the best fitting times for the events are these green bars, and that some of them are small and short and limited to the southern part of Cascadia, which is on the right, and others went the full length and are detectable at all sites up and down the margin. And so we published this, and here's just so you can see a little bit what this messy thing looks like. This is the top section of it. We published this in 2012 and an update in 2017. And even though radiocarbon can never prove synchronicity, the basis for this interpretation is not just the radiocarbon, but the confluence test and the direct correlation, which is the heavy green lines, from site to site, independent of radiocarbon. So this thing began to look to us like a coherent system, and you could treat it as such, with all the parts fitting together in a coherent sort of way to tell a story. And so, if true, and these things are always up for debate, but if true, that means that we can potentially take that ugly diagram and turn it into a series of slides to show past earthquakes and the evidence for them up and down the margin. So this is Cascadia, the movie. This is going to play at about 200 years a second and show all of the 46 earthquakes that have been interpreted in Cascadia. And the various colored dots on here will show for each one the sites where that event is interpreted to have been recorded. So let's start at 10,000 years ago and go forward. Let's see, I think I'm going to have to punch the buttons here. And so all the marine sites are just shown in blue. and there's not much land activity in the early days. We're at 8,900 years or so. And there's not a lot of land sites that record these older events. A couple of lakes in Washington and one in Northern California. And we're at about 8,200 years, coming up to Crater Lake, goes off 7,600 years ago. And now we're coming up to the biggest one of all, T11, this monster 5,900 years ago, recorded at all the marine sites and all the lakes that have been looked in so far. And after that giant one, there was kind of really a dead air in Washington for over 1,000 years, but that space was filled by 5 small events that are limited in length. And now we're up to about 4,100 years. Now you're starting to see more land sites are starting to kick in right about this time. The coastal sites kick in at about T8 time, or 3,500 years. And there we go. There's some of the land sites. So Bryan's site at Willapa Bay kicks in at T8. And now we're starting to see many more sites. And this little thing going off, the little banana slug looking yellow thing going off down there is the San Andreas Fault, which it turns out goes off at about the same time as Cascadia repeatedly, which is an interesting story in itself. So now we're down to about 1,500 years, another 1,000-year gap between T5 and T6, recorded at all sites. So this gap is a linchpin in the record. There goes the San Andreas again. Now we're coming up to the penultimate event about 500 years ago, known as T2, known by us as T2. It is. And then the famous AD 1700 earthquake, which to us doesn't look like a giant. It actually looks sort of average. So the idea that an M9 earthquake is sort of average is a little disconcerting, but there it is. And of course, now the 1700 earthquake was observed in Japan, which we all know now. But there were actually people here, and when geologists began to figure out the stories about Cascadia, the Native Americans essentially said, "Why didn't you just ask us about it? We knew about that," and they did. They just didn't call it a subduction zone earthquake. They called it the Battle of Thunderbird and Whale, and this story was told up and down the region, from First Nations in Canada, all the way down the coast. And so Thunderbird and Whale were their 2 biggest gods, and they got into it, and their stories about this great battle that they had, they were not buddies, involved a lot of shaking of the ground, great shaking, and waves, and the ocean coming in and washing away of villages and things like that. And when you read the stories as they've been told, they sound exactly like a big earthquake and a tsunami. So there's pretty high confidence that that's the story that they were told. And so there were people here, not only for 1700, but for many, many more earthquakes before that one. And the difference, though, between their story and the scientists was that their story had a parable. And that was that if Thunderbird and Whale ever tangled again, be careful and don't build your villages too close to the coast. And so this is a summary of what those 46 earthquakes look like. We have about 20 of them that are approximately full margin. We have a couple that are a little bit shorter, quite a few that seem to stop somewhere in northern Oregon. And our constraint on exactly the length of these things is pretty poor, actually. It's bigger than these uncertainty bars shown here. And a few more stopped in central Oregon, quite a few seem to stop around Cape Blanco here, and a few more are quite a bit smaller than that, and only a single one that seems to affect just only Washington. So somewhere in the middle 90s, this movie 10.5 was made. It was a really, really bad movie, but the premise was something like a big earthquake that that split Western North America, somewhere from like Mexico to Canada, in this giant earthquake. And it's a really horrible movie, but the premise is kind of interesting. And at the time it came out, we were working on not only Cascadia turbidite sequence, but the San Andreas turbidite sequence between Cape Mendocino and San Francisco. And we found an odd thing just about the time this movie came out, and that was that the sequences of earthquakes, about 3/4 of the time, matched up pretty well with Cascadia. And so the gray ones here in this plot are the San Andreas earthquakes, and the blue and red ones are the Cascadia earthquakes. And they seem to match up pretty well about 3/4 of the time. And so we published this paper, and of course nobody liked it or believed it, but we proposed that the San Andreas Fault may be triggered some of the time by Cascadia earthquakes, and that the faults were potentially partly synchronized. And so here's a view looking to the east of Cascadia on the left, and the San Andreas, which is right here. It's offshore in Northern California, on the right, and the sort of channel systems that exist on both sides. And so we went back in 2009 and collected more cores, some of which are shown as these little dots with poles here, to try to test this hypothesis that we proposed in 2008. And so the first thing we did was collect more sub-bottom profiles and more cores and so forth. And one thing we found was that the individual turbidites, which you can see in this image on the left, were actually traceable easily from one place to another. This is about 105 kilometers shown in this figure. And so this is another way of testing the continuity from one place to another. Just trace the bed in the subsurface, and it works pretty well. And so we match these records up to the core, and the details are pretty gory. But we needed to do this in order to improve the sort of tightness of the story in Southern Cascadia to go after this possible connection. And so here are, going back to that view again, here are the primary core sites that we wanted to compare, one at Trinidad Canyon and one at Noyo Canyon. And these sites were really, really excellent sites. And so we worked pretty hard on building the story at those two places. And what we found was that one of the first things we found is that the uppermost event in both places was not the 1700 earthquake. It was an earthquake that happened in 1992 called the Petrolia earthquake. And we could date that literally almost to the year, which you can see that, using a modification of radiocarbon, which uses the bomb carbon contamination from bomb testing from 1952 onward. And it allows you to date young events to within a few years, if they're within a few decades of 1950 or so. So we found pretty clearly that we had a deposit from 1992. And that was a bit of a shocker, because it was only a 7.1 earthquake. And then we worked a bit more on these things and found that at the Trinidad site, we could find Petrolia 1992, the 1980 Eureka earthquake, the faint one there, and the 1906 San Francisco earthquake right there. So we're on the Cascadia side of the system, though. And then there's the famous 1700 earthquake from Cascadia right there. So it kind of dawned on us that if we can record San Andreas earthquakes 100 kilometers away from the end of the fault, maybe the reverse would be true, and we could see Cascadia earthquakes along the San Andreas. And so we investigated this some more, and sure enough, we found that was a good explanation for the timing sequence. And this diagram shows San Andreas on the right, Cascadia on the left. We established a new land site at Lake Merced in San Francisco to help improve the land record. And we found that, as we had a decade before, that these matched up pretty well. These gray lines matching the purple lines with a double sort of equal sign shown in between are the timing matchups between these two fault systems. And so the original hypothesis held up pretty well, but still radiocarbon has big uncertainties, and you can't really prove something is synchronous with radiocarbon. So we thought a little bit more about this, and we found that something that puzzled us for a long time started to make sense. On the San Andreas side, the deposits looked like this. They had a big sandy slug on top of the turbidite. This is the turbidite in a CT scan, and the finer material was at the bottom. Well, this is completely upside down. It shouldn't look like that at all. Usually the sand, this part, is at the bottom down here, but these were all upside down. And the ones that matched up in time, they were all upside down in that same weird way. And so what we finally decided was that these weren't upside down turbidites. This was two turbidites with the San Andreas underneath with Cascadia, the Cascadia earthquake underneath, and then the sandy part on top was the very local to this site, San Andreas earthquake. So this represents two earthquakes very close together in time, measured independent of the radiocarbon. And here's sort of a rogues gallery of all of those matchups, and they all look very similar, with the sand slug on top and the weak parts of the event down below, like these here. And the exception to that, really the only exception, was 1906, the San Francisco earthquake, the only one in this time range that didn't have a Cascadia matchup, and it was a very thin minor turbidite. The rest of them that have the matchups with Cascadia have this booming sand on top. So, and we'll just skip ahead to a little bit. And so here's that in detail then, with the Cascadia event on the bottom, San Andreas proposed event on top. So how much time could pass between these things? Well, it's hard to tell. We can't tell really if it's minutes or hours, but these were close in time, and we see this close stacking repeated again and again and again. So the upper part could erode away the time, the sediment deposited between them, and could get you out to a few decades perhaps. But the best explanation was probably that these were pretty close in time. And so here's, okay. Well, we're going to skip this slide anyway. It's not working for some reason. So, so the bottom line for Southern Cascadia is we have these somewhat smaller events, segmented events that are not nines, that occupy various lengths of Cascadia. Some of these events are probably Petrolia-like, magnitude 7, like the one in 1992. We also have Northern San Andreas events appearing in Cascadia. And then, of course, we have the San Andreas events here. So we wound up thinking that the very close stacking of events supported the original hypothesis that these two faults trigger each other, or Cascadia triggers the San Andreas, and that they've been essentially 70% or so synchronized for the last 3,000 years or so. And so the bottom line of this, when I mentioned a lot earlier about the list of things that can generate turbidity currents, here's the list, full list. And so, how did we eliminate all these things and just go directly to earthquakes? Well, mainly it was by regional correlation and with the confluence test. So we can test for storm loading, wave loading, things like that through regional correlation. The correlations are just 1,000 kilometers is just too long to be a practical, for storms or distal tsunamis to be a practical source. Sediment loading would be just random. There'd be no expectation to correlate. Storm hyperpycnal flows coming out of rivers, also just not big enough to match the correlation. Meteor impact, that's a pretty far-fetched idea. Crustal earthquakes, also too small for the most part to match up the long-distance correlations. But sometimes, for the smaller events, that can work. Tectonic oversteepening of the margin is also sort of a random thing, wouldn't expect to correlate. And the same with gas hydrate destabilization. So just through the long-distance correlations, we pretty quickly come back to great earthquakes as being the best source. So now, where do we stand as humans? It would be great if this was the story, but unfortunately, we have to come to the grips with magnitude 9 earthquakes where we live. And of course, we'd like to know when the next one is, and we can't predict earthquakes at all. But we're fortunate now through the work of Atwater and our work and a whole host of other people to be able to put together that story, that there's enough data to do probability statistics that really mean something. And this is sort of what it looks like. So for the northern margin, and we'll just separate this into north and south, and plot all the data points, which are the blue dots on here, and time across the bottom. If we go out 360 years from the last earthquake and put a target there and say, okay, based on this data, where do we stand? Well, you can see all the blue dots are out in the future for the northern margin. The average repeat time up here is 400 to 500 years, and we're at 322 right now. So it means the average repeat time for us, or for the northern margin, for Seattle and so forth, is still in the future. We haven't got there yet. And that translates to a conditional probability in 50 years of about 10 to 14%, roughly. There are lots of people who have calculated this, and we all get roughly the same result. So for the big M9 earthquakes, that's the probability. It sounds small, 10 to 15%, doesn't sound big. But just for reference, the Tohoku earthquake hit at about 20% probability based on the paleoseismology that we have now. On the other hand, if you look at the southern margin, it's a bit of a different story. Down there, we have 46 earthquakes, and the average repeat time is about 240 years. So that means that all of these blue dots, they're in the past. We've blown by almost all of them, and there's only 1, 2, 3, 4, 5, 6 dots left. So it means that for the smaller earthquakes, the 7s and 8s, we've blown past the recurrence intervals of almost all of them, and there's only a few that were ever longer than 320 years. And so that leaves us with a probability in 50 years of around 37%. And so that's a huge number, and means that, you know, it's very likely that we'll experience one of these in many of our lifetimes. We can also ask other fun questions from the record of if we have a 10,000-year record, how are they spread out in time? And here are two models that show, and so these are the earthquakes, the big ones now, just the big ones, and the height of the bar is an estimate of the size and the timing of them. And so you can see that they're not spread out evenly. We have sort of a cluster of 5 here, and then a 1,000-year gap, and another cluster of 5, and then another 1,000-year gap. And then it gets a little less clear back here. And then this is just a different realization on the bottom of that. So unfortunately, though, now that we kind of know they're clustered, and whether this is statistically significant or not, the statistics say that it is, but we don't know how far back in time this goes. You know, does it repeat reliably again and again and again so that it's useful to make predictions? We just don't know. So unfortunately, this is a neat diagram, but doesn't help us predict earthquakes at all. You know, we could be looking at another earthquake that we're, you know, overdue for, essentially, or we could be looking at a 1,000-year gap, or we could be looking at something else. So unfortunately, we just don't know what to do with this diagram yet. So when it comes to society and great earthquakes, this is a really strange thing to say, but this is actually what success looks like in a great earthquake. So Japan lost 20 to 24,000 people. But a very similar earthquake in Sumatra, they lost 250,000. So they did 10 times better in Japan through being more resilient, better education, better drilling, and coastal defenses and things like that. The reason the number could have been 0 for Japan, except they made some errors in the geology and they got the tsunami size wrong by a whopping big amount. And so all of the damage was essentially done by the tsunami and not the earthquake. If it weren't for that, you wouldn't see photos like this. So when you come back to the Pacific Northwest, you know, a question is, you know, are we more like Sumatra or are we more like Japan? We think of ourselves as a modern country and all that, but we have a lot of unreinforced masonry buildings. In a modern sense, we have yet to have our first big subduction zone earthquake, and most of our cities were built before plate tectonics. And so a lot of our infrastructure is very, very fragile. And honestly, we're much closer to Banda Aceh and Haiti than we are to Japan in terms of resiliency. We've barely even started moving the ball down toward resiliency. We have lots of URM buildings. We have 300 bridges, very spindly bridges. A lot of them are drawbridges, which are just perform terribly in earthquakes because of the big counterweights. We have some spindly bridges like this one across the Columbia that barely look to me like they'd stand up to a strong breeze, let alone an earthquake. So, so we have a problem there, and we also have a problem with unreinforced masonry, not just buildings in general, but schools, hospitals, and things like that. We have 1,000 unreinforced masonry schools and just in the state of Oregon, 3,000 in the region. And we're retrofitting these at a rate of, you know, just a handful per year. And so how are we doing otherwise? How are we doing in terms of getting ready for this coming earthquake? One way to look at this is this. This is Mayor Sato of Minami-Sanriku in Japan, and we visited with him a few years ago. This building that we're standing in front of is the public safety building, where I think 42 people perished staying at their stations to broadcast tsunami warnings. Unfortunately, the tsunami was much bigger than they expected and that the scientists had told them to expect. And so Mayor Sato climbed up the cell tower. He was in that building, climbed up the cell tower and snapped this picture. He didn't snap this picture, actually. One of his colleagues did, of the town of Minami-Sanriku as it looked during the tsunami. So 6 of the people in that building survived by climbing the cell tower. And so Mayor Sato is now pretty circumspect about what he says publicly, but in private, he just says, no more tsunami. He doesn't believe the scientists anymore. And he's busily hardening the town against a future tsunami in some very creative ways. So we come back to Oregon. How are we doing? Well, there's some great examples of forward thinking. So this is the new Seaside School where they moved the school up into the woods, basically on the opposite side of 101 to a safe height out of the tsunami zone. After a bond measure failed, the school kids started a GoFundMe campaign for $200 million and basically shamed the parents into passing the bond measure the second time. And there it is, it's complete. Unfortunately, just as they finished it, COVID hit, and I'm not sure if they're having classes in it right now. But anyway, there it is, a total success story. In Washington, Long Beach, Washington, they also built another vertical evacuation structure at the Acosta School. So 2 really good examples. On the other hand, OSU has built a new marine science building on a sandbar in Yaquina Bay for some really pretty odd reasons. Probably too much detail to go into here, but they were determined to do it, and basically the objective was to demonstrate how to build buildings in a tsunami zone. And around the world, nobody actually does that. They usually try to get out of tsunami zones. But anyway, there it is. And so, the The picture of Mayor Sato is here. What would Mayor Sato do? Would he build a school building in a tsunami zone? You can bet not. And so I'm going to wind it up there. And thanks for listening. And be happy to hang around if you guys have some questions. Thank you very much. Let's see.
Thank you, Chris. I appreciate your taking time in your busy schedule and joining us tonight, as well as everyone else that's out there as well. And when we get Chris, there we go. Hi, Chris. We do have a few questions that have come in. The first one, actually, I got this afternoon. Question for Dr. Goldfinger. I was a member of the Redwood Coast Tsunami Work Group when I was in emergency management in Humboldt. I would like to know if Oregon has organizations like that that I can interact with in my new position. We've got a new emergency management person, Rob Alton, here at SWOCC. So he's wondering if you're aware of anything like that.
I'm not aware of anything quite like that. We have, so DOGAMI, the Oregon Geological Survey, has a very active group that's working on the tsunami problem in Oregon, but it's not a public sort of interactive group the way the Humboldt County version is. I wish we did, because there are a lot of people that could help out in some of these issues. So it looks like there's room for someone to start one.
A couple other questions have been coming in. This one you kind of hit on from Jenna Allen. Do you think you will see this event in your lifetime?
Well, probably not an M9, but if you include all the events that we seem to have a geologic record for, I guess I would say that we've already seen one in 1992. So the Petrolia earthquake would be, in the latest version of how I see things, would be one of those events. So we may have already had our event in 1992. But they're also pretty frequent, and I wouldn't be a little bit surprised at all to see another one of those.
Jessica Regal asked, does the percent and timeline change if we have a huge cluster of small ones that was not I'm guessing not calculated. It stopped. I don't know if it hit a word limit there.
I think she might mean like the cluster of offshore earthquakes we've had recently.
Yeah.
And not calculated. Yeah. So the recent, if that's what she means, the recent cluster of small earthquakes are far offshore on the Juan de Fuca Ridge and the Blanco Fracture Zone, which are parts of the system, but those earthquakes don't either add or take away time from the timeline of Cascadia big earthquakes. They're simply sort of squeaky wheels of the system just operating normally, and they happen all the time.
So one of the general questions that I've been asking speakers during pandemic times, what kind of coursework? We know that there's a number of community college students out there, also potentially some middle school, high school students. If you were in either any of those age groups presently, what kind of classes and potentially other opportunities would you seek out if you were interested in following a STEM academic pathway or STEM career?
I guess I'm going to be a traditionalist and just suggest math and physics and chemistry as well as being kind of the founding blocks of all of the sciences, really. I mean, we all want to, and especially geologists, want to just jump ahead and get to the fun part. But the better foundation we have in those basics, the better off we'll be in the long run. And a little bit of pain up front will pay off later on for sure.
And so this is one of those things that we were discussing beforehand. So one of the things a few years back, originally I was thinking Cascadia quote, but certainly a Cascadia soundbite that still gets kicked around a little bit was everything west of the 5 is toast. Would you like to take a minute and elaborate on that statement?
Yeah, sure. So that quote came out in a New Yorker article in 2015, and it's been passed around and passed around and passed around, and caused people to become irate about it, and caused other people to freak out about it. It turns out it was misquoted. So the person who said that was the Region 10 FEMA manager. And what he was trying to say was, and what he actually said was, our starting assumption is that everything west of I-5 will be toast. And all he was trying to say was that we're going to send all the cavalry, no matter what kind of earthquake y'all have, and not really that everything west of I-5 will be toast. But it's been misquoted and handed down and so on. So there's no geologic boundary at I-5, and no, everything west of I-5 is not going to be toast. It was just a bad misquote and very unfortunate. But it did cause a certain amount of freak out among people, and a little bit of panic is not necessarily a bad thing. It got a lot of people motivated to start thinking about this thing as a real thing that's going to happen.
I think from down here, one of the things that I saw, and again, one of the reasons that this particular talk in the lecture series has become increasingly more important to me when we see the tragedies around the world that take place and the lack of preparedness here. It always worried me, since that was bouncing around, that people just take that as an opportunity to say, oh, we're all done. There's no sense in doing anything at all. And so, I appreciate your comments on that and bringing that back around. And also the sense that we should all go back to the original and not the phone line bounce that continually changes things. Well, again,
yeah, that's right. And that's right. Oh, I was just going to say that the takeaway for me really is not the doom and gloom version of all this, which we've heard from lots of different sources, from National Geographic, from Nova, from the New Yorker, and all that. But what we learned from Tohoku in Japan is that magnitude 9 earthquakes, as big as they are actually pretty tractable things that society can deal with. It's not a throw up your hands and the asteroid is coming situation at all. It's actually pretty tractable, but getting after it and becoming resilient is a very long-term effort that's going to take a lot of people, a lot of resources to make happen, but it is doable.
Well, again, I'd like to personally thank you, Chris, for making time in your busy schedule to participate in the 17th annual Cascadia anniversary lecture. Thank you very much. All of you for attending, and hopefully we'll see you in about 13 days, Tuesday, February 8th, for Sean Davis and Lessons at the School of Hard Knocks, from the ozone hole to global climate change. One of these days, hopefully we'll see you all back live in the Hale Center, but till then, the next couple talks will likely be live streamed as well. But I look forward to seeing you again soon. Take care, stay safe, and have a good night.